Okay, today we'll begin Unit 7, and Unit 7 is going to be all about concept of equilibrium. You may have remembered a little bit about equilibrium back in biology, and we'll revisit that a little bit in this section here. And with Unit 1, 7.1 and Unit 7.2, very similar, so we're going to combine these all in one lecture today. And so you may have, again, remembered your definition of equilibrium from biology class, but we're revisiting that now. Dynamic equilibrium, and the word dynamic is extremely important in this case. Dynamic is going to be that it never stops. Things are going to be constantly moving. Now, it may be moving in one direction at the same amount it's moving in another direction, so it's as if you don't notice it happening, but that doesn't mean that nothing's going on. So equilibrium is it is about kinetics, about their forward and reverse reactions and how fast they are going. So they can be about physical changes, and we can represent that looking like a chemical reaction or actual chemical reactions. It doesn't have to be just redox and acid base. I just listed a couple here. But these were equilibrium processes. You could take liquid water and boil it, but you could also take gaseous water and condense it back down to a liquid. And you could keep going back and forth between those two all the time. And there are times where the forward reaction is happening at a faster rate than the reverse reaction. There's also times where the reverse reaction is happening at a faster rate, and I'm just representing faster and slower by the size of these arrows here. And the forward reaction may not be going nearly as fast. So you would realize, if this was the case, condensation. If the one I had before, you'd notice boiling. So those give you at least a starting point about chemical equilibrium. And again, I said dynamic because everything is still moving. And I threw this one in here, aqueous solution, because this is where it was represented in biology, osmosis of water, movement of water. So I guess here's your semi-permeable membrane, and some things can go back and forth. It looks like the water's not, well, water's going to be moving also, but it looks like we have actual some sort of dye or dyes that are moving from one side to the next. But eventually it will reach a dynamic equilibrium as movement is left to right, movement's right to left. So you won't actually see any differences with these solids. Yeah, so osmosis, and you guys talked about this back in biology class. But we're going to talk in terms of chemical reactions mostly, but still some physical processes. So in earlier sections, we were very interested in this region of the graph where the kinetics of the forward, well, we didn't study the reverse reaction because not all reactions are reversible, but as reactants get used up, the reaction typically goes slower and slower and slower over a period of time. Well, now in equilibrium, we're going to be interested in when these level off like this. So concentration over time, those rates flatten. That is now equilibrium. So the forward reaction and the reverse reaction are happening at the same speed. This is just a little bit of different representation of the same idea there. When the lines are level, is equilibrium reached? Yes. When equilibrium is reached, does the reaction stop? No. Remember the term dynamic. So the forward reaction moving left to right, and the reverse reaction moving right to left is happening at the exact same speed. So what happens to the change of the concentration of the reactant? Well, I think it means at equilibrium, which would be at 60 seconds and past, as long as you don't do anything to the reaction, change the temperature, change the volume in case these are gases, change the pressure in case these are gases, add more, subtract some materials. As long as nothing like that happens, these concentrations will remain the same. So as one material goes from reactant to product, another material is going from product to reactant. Same representation again. It's hard to tell exactly, but it looks like this. They've decided it's at this dotted line is where dynamic equilibrium has begun to occur, and both these just show you that the amounts, the concentrations, brackets mean concentration, by the way. They definitely, at certain times, maybe it favors more going right to left. I'm sorry, left to right. And then sometimes, depending on what the conditions are, the reaction is more favored to go from right to left. And what that really means is at the end of the day, think of it like a teeter-totter, a seesaw. This would be, I guess, kind of represent that at the end of the day, it's a 50-50 between left and right. Well, there's some of these instances where it might be more like that. Or there's other times it's going to be more like that. And we'll have to study how to indicate that. What do we do with those different things? Well, we'll see what happens here in the next couple slides. Okay, so we mentioned the kinetics of the forward and reverse reactions are the same at equilibrium. Reversible reaction can proceed in each direction. We talked about that. They may not have the same rates. And then we're going to represent this equilibrium concept with capital K. Now, people use all kinds of little designations for subscript here, depending on what kind of equilibrium they're talking about. That little c, you might think it stands for constant. Typically, I think we would use those more for concentrations. So it would be solutes that are dissolved in solvents. We can have a Kp that would deal with pressures. Some people even go a little further and go Ka for acids, Kb for bases. There's all kinds of different Ks. You might even be able to find a textbook somewhere that might call it KEQ. But any of those, they're all the same. They're all the same. Well, we will find one difference as we move forward. There is a relationship between Kp, which deals with pressures, and Kc, which deals with concentrations. So we will visit that. I don't think we're going to do that today, but another section. If you wanted to go between kinetics and equilibrium, that's what you'd have to do. So K, equilibrium K, capital K, equals the kinetics, that's the rate law constant, forward versus reverse. Okay. You might have a multiple choice, might have a free response 1 point part of a question where you might have to plug two values in to get a third value. Move this up a little bit. And what does K represent? So you have some reactants, you have some products, and what are you going to have more of at the end of the day when it reaches equilibrium? If the K value is larger than 1, you're going to have a lot of reactants become products. Not all, but a lot. If K is less than 1, you have actually, let's go back to the K is greater than 1. You're going to have kind of this representation. No one writes this, but think about it this way. There is a few products that become reactants, but most of the reactants become products. So at the end of the day, you're going to have a lot more of the products. And then if K is less than 1, it's the opposite idea. There's not going to be many reactants becoming products, but there's going to be lots of products becoming reactants. So at the end of the day, you're going to have a lot of that. So not many of the reactants will become products. That's what you'll notice. So let's jump into a couple questions here. So here is our graph that's going to go with the question, and then here's what we have to answer. So this question is going to be about what's going on between T1 and T2. Well, that's T1 to T2. So what's going on there? We just learned that when those go horizontal, those graphs, that's equilibrium. So we're looking for one of these answers that kind of deals with equilibrium. And I don't know about you, but when I see the word equal, that often has something to do with equilibrium. So the rates of the forward and the reverse reactions are equal. So that's going to happen when concentration versus time gives you those flat lines. Anything on this part of the graph is going to be where we studied kinetics. So the reactants are going to go down in concentration over time. The products are going to go up in concentration over time. And we've kind of learned how to study those in previous units. Question number 2. Like most of these, we already have an answer, but let's figure out why. By the way, this is a really interesting reaction, and the reason it's really interesting is this material here has a very distinctive blood red color. This has a very, very, very faint yellow. Depending on its concentration, you may not even be able to see that it's yellow. It might look, all this might look clear to you. So I'm going to even erase this, and we'll just put clear here. So you can kind of get an indication about, does the reaction go more reactant to product and become blood red, or does the reaction remain fairly clear, and that means that more of the right to left action occurs. Okay, so remember I was telling you that sometimes you might even see KEQ. Capital K is equilibrium. So it gives us a value. So what does 240 mean? 240 is greater than 1, which means lots and lots and lots of forward reaction and very little reverse reaction. That's what 240 means. And are we going to need that for this question? Well, we already know the answer is B. Let's see what B was. The product is favored over the reactants. And that's correct. So if you have an equilibrium number of 240, you're going to have a solution that looks very, a reaction solution that's going to look very blood red. If the K value would have been 1 times 10 to the negative 8th, yeah, we'll do negative 8. That's really, 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 really small. So in that case, here's our test tube with the chemical reaction going on. This is probably going to be clear. Okay. But we didn't have that one today. We had 240. Question number 2 of 3. So our question over here on the left, and our answer is on the right. Yeah, we already have an answer. Okay, so we have this material here that decomposes into 2 new materials. A pure sample of PCl5 is placed in a rigid evacuated container. So the container at the beginning only has PCl5 in it. So there's only one thing that could happen. You could only have at the initial, as soon as the reaction begins, you could only have left to right going on because you don't have any products to make back to reactants. The initial pressure is 1 atmosphere, temperature is held constant. The reason the temperature is held constant because if you change the temperature, then we have a lot more to deal with equilibrium, because temperature can affect lots of different things like the pressure of gases from gas laws. And then it reaches equilibrium. Okay, so we actually get to the point where the forward and reverse reactions are the same. The figures below show the initial and equilibrium concentrations of the system. Do we have all that? We don't. And where do we have that on? Did I have it on a different slide? We don't. So let's go. Maybe we didn't need it. Let's check it out. Oh. No, we don't have. I think there was some other questions that you did need some other information, but to answer this particular question, I don't think we're going to need that. As the reaction progresses towards equilibrium, the rate of the forward reaction. So if you remember, we had some graphs. So reactants are these things. So now in this case, there's 2 reactants, but they go down in concentration and their rates go slower and slower over a period of time. The product, on the other hand, you start off, in this case, 0, and it moves up in concentration, but the speed of that happening decreases over a period of time. So we might be able to use that to answer this question. So the reactant decrease the rate of the forward reaction, the PCl5 going to PCl3 plus Cl2, decreases over a period of time, and it's never going to get to 0. It will not get to 0. It'll approach 0. Whoops. It'll approach 0. Okay. And our third question, still the same reaction, but now it looks like we have to look at something graphically here. Additional Cl2 was added. So now we have a situation. Here's our, let's make a flask over here. And we have in this flask PCl5. We have PCl3, and we also have Cl2. That's all at equilibrium, meaning that there is a forward reaction and a reverse reaction taking place, and those are happening at the same speeds. And as long as nothing else changes, that will stay exactly like it is, again, until something changes. And what's changing for our particular question, that's going to change. So they have decided they're going to add Cl2. So think of a teeter-totter seesaw, and you have a situation where maybe, let's make it perfectly like even. That's going to stay like that until something happens. Well, maybe you add a couple more weights over here. Well, if you do that, it's not going to stay the way it was. It's going to reposition itself until it gets to a new equilibrium. So with this situation, if you add more products, so let's use an arrow there, you now have more Cl2s to fly around in that container, and more of them are going to hit the PCl3s that you have in there. If more collisions are taking place, you now have more opportunities for those to to come back and make PCl5. So if you add more products, in this case Cl2, you have an opportunity to move the reaction more right to left than it was before. So what would that look like graphically? So first of all, equilibrium, you have to have that happen. So we can't have this. We need that rate to have a horizontal section. Then it says you're adding Cl2. Well, if you're adding Cl2, you have to be adding Cl2. So you would just dump it in. If you dumped it in, it gets put in very, very quickly, not this over time. So we've eliminated those two. We're down to now B and C. Now, if you add Cl2, is it going to come back to equilibrium at a higher spot than it was before, or a lower spot? And I like to kind of think about this in terms of a bathtub. It doesn't have to be a bathtub, just any body of water. Okay, so here's my bathtub, and I have a level of water in there. Those water molecules are moving all the way around that bathtub or whatever vessel you want it to be, and that is a dynamic equilibrium situation. And that level of water is right there. It's not going up or down. Pretend there's no evaporation going on. Then if someone adds some water into this spot, what happens to the what happens if you were going to graph this? So we have the water here. I just added a bunch of water. It goes there. And then what happens to that water now? It has to spread out into the rest of the container there. And what's going to happen to the overall level of the water? You may not be able to notice it, but it's going to go up just a little bit. It's certainly not going to go down to like that level if you added water. So what does that look like? I think that looks like B. And that might be it. Yeah, that is it for today. That concept right there in this particular question, if you didn't quite get all that today, don't worry. We're going to have many more sections of this Unit 7 that we're going to study this phenomenon with a lot more detail.